All right, I think that's as much as I can play. Hi guys, welcome to the March 30th video. I should pause. There we go. I'm here at Pride Rock, and I've invited a special friend to help me talk about the models that we're going to be talking about today. And specifically, what we're going to be talking about is modeling with systems, and we're going to be using a very specific example. Okay, so we're going to tell a story about rabbits and foxes. So here's a rabbit, and what happens when several rabbits get together is they make lots of rabbits, so rabbits multiply. We can presume that there's plenty of grass and the whatnot for them to survive. If there's an unlimited amount of supplies to survive, then basically we get this sort of situation right here where the R is rabbits and G is some growth rate, and we can have exponential growth that results from that. Or we can use the logistic equation here where our little k, remember, is like some sort of carrying capacity. Okay, so underneath that, the population of rabbits will grow and then flatten off, or above it, they'll crash down to their carrying capacity, like what we can see right here. Okay, another animal that we are going to evoke in this are foxes. That's a very cute fox. All right, and then without other animals to eat, foxes are going to die off. So we've got this number D here, the rate of dying off, and there's a negative sign in front of it to denote that we've got this decline here, an exponential decay. And that would be a problem for foxes, except we must remember, when it comes to rabbits and foxes eat rabbits, okay? And that's the big point of why you want to model with systems, is that you recognize that there's some form of interaction going on between at least two of your state variables. Thank you, Mufasa. You can go. Okay, great. So if we take like the idea that foxes and rabbits are these two little populations, what we are really assuming is that foxes will influence the rabbit population, and the rabbit population itself influences the fox population. So we'll take two of those models. We'll take the simple exponential growth for rabbits, okay? And then what we want to do is we want to add on particular rates. And so the rates that we're going to add on is minus CRF onto the rabbit equation and plus ERF onto the fox. And so we really need to kind of get our head around, why are these the terms that we're putting on, okay? Because this is supposed to be how these two populations are influencing one another. So the first question you should ask is, why is it R times F? Okay, so I want to try to paint a little bit of a story. This is an imprecise explanation as to why it would be the product, but I think it's good enough for our purposes, and we'll really kind of get at kind of what's going on. So let's suppose, I think I draw 4 or 5 rabbits here. Okay, those are all rabbits, I swear. All right, I've been playing a lot of Pokemon. Those are close enough to rabbits. Okay, so we have 4 rabbits, and then we're going to have 2 foxes. Okay, and so the first fox, let's go ahead and use an orange pen. The first fox can interact with the other 4 rabbits. That's a possibility. I have trouble drawing lines here, okay? But I'm going to draw a line for each interaction that's possible, okay? And since it's instantaneous at that very same moment, the other fox, which we're going to use red for, could also interact with each of those 4 rabbits. So if we want to count up the number of possible interactions that could occur, we basically take the number of interactors, let's say the foxes, and the number of interactees of the rabbits and multiply it together. And so we could have a total of 8 interactions here, given this. Now, I understand there's some double counting and things of that nature. That is some of the imprecision when we atomize this, when we say that R and F are actual counts. But that's okay. This will suffice for now. Okay. Another question might be, why is C not equal to E? And I think the big point here is that being eaten is not in a one-to-one correspondence with babies being made in the eater, okay? And I think we can all understand that the calories and nutrition and whatnot that would be provided by one rabbit does not itself equal what is needed to sustain 1 unit of fox, okay? So we're going to remember C is consumed or consumed by, and E is I've eaten. Okay, and these are the different rates. They have different values. As a good thought experiment, you might want to think about which ones make sense in biological situations for when E is greater than C or C is greater than E. That might be a good little exercise to do. What's important to note here is that C and E, both in them contain the rate at which these encounters actually occur, in addition to some sort of valuation of the benefit or detriment that that counter incurs on the respective populations. Okay, so in order to get an understanding of what's going on with this system, I want to first think about the geometry of this rabbit-fox space, because that's where we are right now. We're in rabbits is 1 count, Foxes is another. We're not in any sort of like distance or velocity sort of thing. And this is where multivariate calculus might come in handy. I want to create an A vector for animals, okay? The first entry is going to have my rabbits. The second entry is going to have my foxes, okay? And so I can think of the derivative of A, which is the derivative of both of those guys, because it's derivatives. I don't know if your teachers ever really mentioned it, but like it's a linear function, which means that it affects everybody in a way that would be sort of the same as multiplying a number and using the distributive property. Okay, so the derivative of my A vector is indeed the vector of the derivatives of each of those terms. And so I can just write down the right-hand side of my differential equations right there. The growth rate of the rabbits times the rabbit population minus the rate at which rabbits are consumed by foxes. And then we can have the dying off rate of my foxes plus the eating rate at which rabbits are eaten by foxes. And then we've got my two differential equations up there. Okay? And the reason that we're going to multivariate calculus here is we want to think of this as sort of like a vector field. All right, and so what that kind of means is we want to think about a vector valued function. All right, so like a function v that takes in r and f and spits out these rates of change. And so what that gives us is then we can be sitting in rabbit fox space, knowing how many rabbits and how many foxes there are right now. And then this vector valued function tells us, hey, this is the direction of your change. You know, maybe your rabbit population will increase and your fox population will decrease. So go in that direction from here. And that's sort of what I want to sketch out right here. Make that an F. It's an F, not an R. Okay, there we go. I can't reach across my paper. It goes into the void. All right, so we just kind of marked out 1, 2, 3, 4, 5 and mark off the F-axis, please. And so what we're going to do is we need to prescribe values for G, C, D, and E. And then we need to think about particular values for R and F that we can plug in. I do this in a slightly different order in the video, but if I mess it up, then I have to erase it and start over again. So we're going to consider first the scenario where there are 2 rabbits and 1 fox, or 2 units of rabbit and 1 unit of fox. And we're going to go ahead and just choose some values arbitrarily. These are indeed the values that are in Blanchard, but I'm just using them for the simplicity of double reinforcing an example. And when you plug those in, you get about 1.6. And remember, that's a DRDT, the rate of change of rabbits, and 0.8 for foxes. So that means if you start at the point 2, 1 over there, then you can expect a growth of about 1.6 in rabbits, and then about half as much in foxes. Okay? And remember, that's an instantaneous growth. So I can just draw a little vector there, and that's sort of the direction of the flow off of that point. Right, we can continue to do this for several other points. So I think the next one we choose is, I should have my notes in front of me, v of 1, 1. So if there's 1 of each, and you get 0.8 growth, but you get this negative growth in foxes. And so here my vector will be pointing down, but quite a bit more it'll be pointing to the right. So it's a gentle lower right sweeping vector, like what I've drawn right there. And then last, I think we do v of 0.5 and 2, 2. So we have, can't have half a rabbit per se, but it's half a unit of rabbits. So you can think of this as like some sort of weight or biomass or something like that. And we see that both populations are decreasing here in this scenario, and the foxes are decreasing much more rapidly than the rabbits are. So we've got a very steep downward pointing arrow here. Okay. Now, what you can do is you can just continue to do this. You pick a bunch of various points throughout this RF plane, and you draw arrows based on what the vector field tells you. And this gives us a feel for sort of what's the flow of the dynamics in this space. And there's a few things that I want to be able to point out when all is said and done, and you've got something that feels like a rather complete vector field. One thing of note, sure we'll use red, is this inner part right here. If you plug in values, you'll find that all the arrows are much smaller than arrows further away. Okay, and so that means we have far less movement in the middle there. We've got just these small changes versus these broad sweeping changes. And then you'll notice as you get closer and closer to the R-axis, your vectors are more flat horizontally. And closer to the F-axis, your vectors are more flat vertically. And so this gives us some zones and some things to think about for various thought experiments with respect to, can I analytically make some sort of assessment of what's going on in this system. So I'm going to once again draw my RF plane. I'm not going to bother putting the tick marks or anything like that. And for my very first thought experiment, okay, I want to assume, I forgot which one, okay, no rabbits, that we are close to that we are on the vertical axis here, okay? And so that gives us where my flows were very kind of sharp up and down. So if r equals 0, then r prime also equals 0, and f prime equals negative df, okay? So there's no rabbits to feed the foxes, and there's no rabbits to make rabbit babies. This means r of t is technically whatever the initial value is, but we said already that r of 0 equals 0, so we never have any rabbits regardless of the time, and my foxes experience an exponential decay. So what I'm going to do on my diagram here is I'm going to put several just downward, straight down arrows on that F axis there. And so what that's going to denote to me is that if I start on that axis, I stay on that axis, and I just flow straight downward. Okay? My next thought experiment will be sort of the converse of this, where I think kind of horizontally. So let's say there's no foxes around. Okay? So that means my rabbit population just experiences growth. They don't care. They're not getting eaten, whatever. And so we just have this exponential growth of r0e to the 2t. For my fox population, there's no foxes to die. There's no foxes to be born from fox-rabbit consumption. So my fox population will always stay 0. So to mark this, I'm going to stay on my horizontal axis. But now instead of shrinking toward the origin, my rabbit population is growing. And so I'm going to put some right-facing arrows leading out. Okay. Now a big question might be, what happens if I start on the f-axis? Do I flow downward, hit the r-axis, then flow outward? Because that would mean that I started out with no rabbits, my foxes go extinct, and then spontaneously I get rabbits. Well, what happens at the origin when r equals f equals 0 is both of my differential equations are equal 0, which means there's no change, which means we're at an equilibrium point. All right, so we cannot actually pass through there. My foxes decay down to that point, or my rabbits grow away from that point if we're on either of those two axes. Okay, I want to imagine an initial condition out here. I have some trouble drawing this, so I have some time to talk here because it's a problem, okay? But it's going to try to sort of follow the flow of these arrows. And the way you want to think about it for now, we will make all of this more precise later, is that if I'm closer to sort of one of these known pushes or pulls, the known decays or growth, then that's the one that's kind of driving the situation. And what we will show in much greater detail later on is that we get this sort of cycle that flows around. It's not quite a circle of life, but it's a closed orbit of life. And we'll talk a lot more about closed orbits later when we decide to get into technical. This is just to introduce us. Okay. And we should remember this corresponds to my vector field having very long and flat lines. And then as we get closer and closer inside, those lines get smaller and smaller and smaller. So we have these tighter and tighter closed orbits. The question is, what's happening on the inside when things are getting very small? Okay. And so we can ask ourselves, well, maybe there's a point in there. Like my circle gets small enough that I've retracted to a point. So I want to look for another equilibrium point. And that's RF pair of values where both of my differential equations are 0 at the same moment. Okay. So I'm just going to factor my rabbit population out of my R equation and my fox population out of the fox equation, set them both equal to 0. We get r equals f equals 0 again, which we already have. But we also get that f can equal g over c, and r can equal d over e. We get those by solving the other two terms. Whatever numerical values you plug in, that's how you're going to get another equilibrium point that sits in the middle there. So if your population stays right there, they will remain there static. Otherwise, they kind of go around this push and pull. Now, this is a phase-space description that doesn't quite tell us the full story, so I'd like to look at some time series for these sort of things, okay? So I'm just going to make a quick and ugly sketch of the cycles again in my phase space just for reference. All right, and let's go ahead and make an axis for rabbits versus time. Okay, so now we don't see how foxes change with respect to rabbits, but we see how rabbits change over time, and we'll also be able to see how foxes change over time. All right, we're going to pick an initial condition just somewhere on one of these curves. I'll pick the big curve. And if I move through that green region, what's happening there is my fox population is not changing very much, but my rabbit population is undergoing an explosive growth. See that? It's fairly straightforward. Now, if we look at, can I get the highlighter back, please? I already said what I wanted to say. I wasn't drawing. Okay, there we go. Change it to orange. My son was talking to me when I was making this. Okay. If I look at that zone right there that I'm trying to color in, my rabbit population is not growing too much, or my rabbit population is not really shrinking all that much compared to the explosive growth or shrink that's involved in my fox. And similarly, that green denotes, again, small change in fox, larger change in rabbits. We get something that looks like these oscillations. And it's going to be a periodic function because we're just traveling along this orbit over and over again. All right, now if I want to highlight the various regions where I have steep increase or decrease, that corresponds to the green regions. And then if I have shallow increase or decrease with the rabbits, that corresponds to my orange. Cool. Now, if we go to draw the foxes, what we should notice is that when rabbits are undergoing explosive growth, generally speaking, foxes aren't experiencing that much growth, and vice versa. And so what we end up getting is a periodic function that looks extremely similar, but it's a little bit lagged. Now I'm drawing it here on different axes. It doesn't quite show you the lag good enough, but what it does is it gets rid of the fact that rabbits and foxes are probably on vastly different scales, frankly. But we can see how the orange now corresponds to rapid fox growth or shrink, and the green here corresponds to the slow growth and shrink in the fox. So it's a bit opposite here. Okay. If we draw those on the exact same axis, this will give us a slightly better feel for how the foxes are lagged behind the rabbit. So I just draw a quick rabbit curve here, and then the foxes are going to be sort of, as the rabbit population increases, the fox population can then catch up, peak. As the fox population peaks, the rabbit population starts to decline, vice versa. So you get these offset periodic functions. You can also see that by studying one of the closed orbits. Do I nail it in one try? I do nail it in one try. It's beautiful. Pick an initial condition here. Let's start with very few foxes and very few rabbits. There's very few foxes, so not a lot of predation can occur. So my rabbit population starts to rapidly increase, while the foxes are just kind of keeping their own. We reach this sort of critical value where now the foxes can kind of have plenty to eat. My fox population is going to start to increase. And up until a point now, my fox population is still going to increase, but my rabbit population now can't take it, and they start to die off until my foxes peak. When my foxes peak, there's so many foxes, there's not enough food for them. The fox population is going to crash, and then after that crash occurs, my rabbits can catch up. And this is a beautiful screen to end on. I'm so glad that that's there. Thank you guys. We're going to have another quick video on mass spring and then something else. Sorry for the delay in this video. My family did lose a cat day or two ago, so it's been rough. Enjoy yourselves, stay sane, see you guys later.